Well, today I'm going to talk about measurement in war, which has been the subject of great developments in the last 30, 40 years, and fortunately has had spin-offs into peace as well. And of course, one of the most important things that you wish to know in war is where your enemy is and where you are, of course, and that is not always clear to you under difficult circumstances, and particularly how either to get to him or to dodge him if you feel you have to. And one of the most powerful methods when applied is that we saw in the last lecture of triangulation. Remember, in triangulation, we were using it for surveying, for finding the distances to stars, and so forth. And you can use triangulation in warfare to establish the position of your enemy if you can observe from 2 points. And the first application that I would like to describe to you was the one used by the Germans against us in 1940, when, if I can have the first slide, they had obviously anticipated World War II by setting up 2 stations each of which would direct a beam over a target in England, and the target would be defined by this beam coming out from here, pointing in this case in the direction of Derby, and the pilot flying along the beam will get a warning that he was approaching Derby, or in fact over it, by hearing this cross beam. Well, when the Germans advanced into France, the situation was much more favourable to them, and they now could direct beams from Cherbourg, or near Cherbourg, with cross beams coming in from Calais. And so what the pilot could do, if they could sight this beam correctly, was to fly along it, receive an early warning from the first cross beam to get ready, a second cross beam 20 kilometers before the target, which would tell the observer or bomb aimer to start a clock running. 15 kilometers further on, another beam to cross, stop the clock. That automatically gave the information about the speed of the aircraft. It was on the right course, and if you knew the height, which you could measure on the altimeter, you could feed that information into a tiny mechanical computer, which would then tell the correct point at which to release the bombs to strike the target. Now, you see, although this perhaps doesn't look like triangulation in the first place, it really is, because you're effectively using the baseline between Cherbourg and Calais, like that, and having known from surveys where Coventry is, you can set up the triangle to get the necessary intersection. Now, radio waves are relatively long, and they don't give very sharp beams, but the next slide shows the way in which the effect of the beam could be sharpened enormously, and at the same time giving the advantages of having a broad pattern. So here, down at the transmitter, in this simple case, one has 2 aerial arrays pointing in slightly different directions. Only one transmitter, though, and it is switched from this to this one, alternately. for a short time on this one, giving a dot, a longer time in this one, giving a dash. So if you're over here, you just heard dots. If you were over here, you just heard dashes. If you were in this region where the two signals were almost equal, you heard both dots and dashes, and when you were perfectly in line, the dots came up to the same strength as the dashes, and all you heard was the continuous tone, and if you were doing that, you were all right. If the dots came up, you know you've got to steer to the right. If the dashes came up, steer to the left, and bring you back onto the beam. Now, we can't simulate exactly that in the lecture room here, but we can, with the aid of a volunteer, show the kind of problem they presented to the pilot by having the equivalent of a beam along here where we've laid a strip of aluminium foil, as you see, against this rather darker mat underneath. And the vehicle here, which is actually a model of a tank, but we're going to make it look like an aeroplane by putting a model of a Dornier 17 on the top. And the object is to fly it along this beam, getting right-left signals, not dots and dashes as the German pilots got in their first models, but the strength of the two signals on each of these two indicators here, the left, too much the left, too much the right. And the signal is not given by radio, but by the difference in the reflection coming back between here and here, in the case if you're too far to the left, here and here if you're too far to the right. And so we'll let our volunteer try and fly the aeroplane along the beam. And he's looking at the indicator, you see. And when he's getting off course, he's well, shall we bring it back on course again to let him... Oh, sorry, Bill. To let him finish it. Right, aircraft shot down, but bombs hit the target. Thank you very much. That was in some ways more difficult than the German pilots had, you see, because they had quite big areas on either side into which they could stray and know the direction in which to return. Well, that is one of the relatively sophisticated applications of triangulation. And remember, I told you that in scientific measurement, sometimes a bit of ingenuity and going back to very elementary methods may indeed produce results that would be very difficult to obtain, even with very sophisticated aids. And there's another example, in fact a double example of triangulation that I want to tell you about, used by the Royal Air Force in World War II. And how many of you have heard of the Dam Busters? How many of you have seen the film? Well, you'll know the basis of the story. And indeed, we have a model here which we'll let a volunteer again drop a bomb and try to blow up the dam. And here you see we have a model Lancaster. Here we have a model of the Mona Dam. And all we can do is to, we can't fly the aeroplane, at least we can control its height, and control its height by the technique which was developed, very simple technique, triangulation again, as it turns out. The length of the bomber being used as a baseline, and the two beams from the two projectors coming down on the surface, because it was essential that the bomber flew at a very precise height, which we'll go into in a moment. And the height, just as we were measuring the range of the top of the lecture room the other day by two lights crossing, here we moved, or someone very expertly moved the images to coincide with the plane at the top there. Here one had fixed directions and actually raised or lowered the aircraft in height until these two patches of light were side by side. Well, let's have the patches of light.
They're on now.
Are they? Yes. Yes, until, and of course it was very dark, but at least moonlight. I can't see them very well, but one is here and one is here. Now, if you, right, and the rule was, you see, yes, go a bit below for a start, if you would. You see now the one spot is behind the other. When it was too high, the order was reversed, and when at the right height, they should be alongside one another, making rather a figure 8. There we are, and at that moment, if the bomb were released correctly, well, may I say that we had taken a leaf out of the Germans' books in the meantime, and we had used triangulation in order to define positions to targets very precisely, but we used a radar system which involved flying the aircraft on a constant radius from one ground station and measuring its position along the arc of the circle by measurements from a second station. It's again triangulation, and because you can measure time intervals so very precisely, it turned out to be the most accurate bombing aid of them all. But going back to the dam busters, we have in the audience one of the most famous of all the dam buster pilots, then squadron leader Martin, now Air Marshal Sir Harold Martin, and I'm going to ask him to come forward and tell us a bit about what the raid, what the techniques were actually like. And here is a picture from which he can explain the main features. And Vicky, there we are.
Well, there were two problems, both of which were solved by triangles. One you've just seen adequately described on the model with the lamps, and the other one was the distance back from the wall that this thing, the bomb, I presume you can see it, should be dropped. Now here it is falling. De facto it was released from the aircraft somewhere back here, and then there's a forward pitch. When it hits the water, it will bounce up again, and then down, splash, and on and on and on. And each one of the bounces will get shorter and shorter. Now, why do we want them to get shorter and shorter? Well, the answer is that we want them to want the weapon to go over the anti-torpedo booms, which were thick, strong, and heavy across here, but not to go over the lip of the dam. So we want the bounces about that high, so hit the lip, rebound back into the water, sink, and go down the face of the water face of the dam, and there be detonated by a hydrostatic fuse. Now, as the bomb detonated, of course, it naturally sent up a huge column or spout of water into the sky, and that became something of a hazard, but I'll come back to that in a moment. Now, the problem was, how were the aircrew and the bomb aimers in particular to establish this point back here to know when to release? And so a retired wing commander took the measurements of those two towers, established the distance on graph paper, drew a line back on the graph paper according to scale for 620 yards. And so we have a triangle, an isosceles triangle. And you will see that if we make or transpose from that piece of paper that triangle onto a piece of plywood, you've got a similar triangle. So what do? You're the bomb aimer now. You're in the front of the aircraft and you're coming into bomb. And so you've got the sight here in front of your eyes, and in the murk in front of you, you'll see the silhouette of the dam wall. And then the two towers will come into view, with the two towers on the wall, and then you'll peer through here, and then they will appear in the middle, and then as you get nearer and nearer to them, so they'll get bigger and bigger and bigger, and then move sideways and sideways, until eventually they will eventually they'll coincide with the nail. And that is the time to press the release button and the bomb will fall away.
And at that point, you'd have been travelling at 220 knots?
We were travelling at 220 knots, and that I think translates.
And so it's
into
just a flash past you as this thing
Very
comes
quick
up.
decision.
Yes. And the height?
The height was 60 feet. And the reason 60 feet was chosen was that we did the earlier experiments down at Recalva lower down. And in fact, I myself dropped one of these things, an inert one, at 50 feet. But when it hit the water, the splash came up so high and so quickly that it tore the back of the tailplane here. And so we had to move the height from 50 feet up to 60 feet. And that gave just enough clearance, about 7 feet from the trailing edge of the tailplane to the water spout.
And that is your aircraft going in?
Well, this is Robert Taylor's depiction of my aircraft,
And
yes.
that's Guy Gibson.
And that's Gibson's, yes.
Up there. Now, another interesting point was that because there had been so much disruption caused by the water explosion, you couldn't go in at closer than 3-minute intervals?
Correct. When the weapons detonated and this huge column of water shot up, it hung for quite a while, and the water drops and globules were too heavy to fly through, at least risk your aircraft against. And also, the spray affected visibility, so that the next aircraft in, or the bomb aimer, would not have been able clearly to pick up the towers in the distance. So we had to wait, and this was as a result of measurements done back here in England, 3 minutes before each attack. And Gibson, in this aircraft, had a look at what was happening near the dam wall before he ordered the number 2 in, and then myself as number 3, and the number 4, and number 5.
So he had budgeted for staying more than half an hour over the target to cover all aircraft in. I gather it wasn't quite as much long as that, because after 5 bombs the dam went, fortunately. In the meantime, you yourself, how did you judge the straightness of your aim, because you couldn't see it from the front?
Well, the pilots just simply lined themselves up between the 2 towers and flew straight between the towers and then over the other side.
And the bomber, but the tail gunner, he saw the splashes.
And the tail gunner saw the splashes because the first splash was just behind him, the next splash was just behind him again. The aircraft had moved on and the weapon had moved on, but it was losing speed vis-a-vis the aircraft.
Yes. And you yourself were hit just over the dam.
We were hit by some Bofors guns, which were just below that wall, shooting up, and there were other Bofors guns here. And we were hit in the central tank here on that wing. And rather gave me some concern as we went through, but there was no fire, so God was kind to us that day.
And you and Guy Gibson stayed together. He looked to see whether you were on fire or not.
He was in front of
Yes.
us, and he swung,
Yes.
and we pulled up behind him,
Yes.
and then made runs down the side of the dam to try and draw the flak and douse it, if we could, so as to give the succeeding aircraft a
Yes.
clean run through, cover-free run as is possible.
Well, thank you very much. Well, it's been a tremendous privilege to have the Air Marshal with us, and I know he'd want me to say that neither he nor I desire to glorify war. We saw far too many brave men and women killed to want to see anything like it again. But I must say, at this point, that he and his squadron, and indeed his comrades in Bomber Command, were among the bravest group of men it was my privilege to support. Their losses were such, they lost 8 out of 21 on the Dams raid, in that single raid, but in Bomber Command as a whole, there were about 100,000 airmen and 50,000 of them were killed. And it was my privilege to at least try and stop those losses going any higher. But Mickey, thank you very much for coming along and telling us, and I hope you will stay for the rest of the lecture. Well now, there was a simple case, and let me emphasize that one of the beauties of this thing was, again, it was triangulation, you see, but it was triangulation the other way around. You used the two towers on the, and if we can have the next slide, I happened to be in Germany about 6 weeks ago and was staying very near the dam, and here is the dam, now of course restored for a long time. Here were the two towers. Here was the central section which was blown out and has been restored. You can just see it is a bit darker than all the rest, like that. And it was these two towers which were effectively the baseline, and the triangulation was used the other way round. Now, you used the enemy's baseline and found your correct point by the angle that his baseline subtended at the point where you were. All very easy to talk about in principle, but not so easy when you're there. Well, going on with military measurements, if I can have the next slide. Besides the beam systems and simple radar ranging systems, we'd already seen in the last lecture the way you could use time differences and hyperbole, and the kind of pattern we were getting, I once saw exemplified in the ornamental pool in my laboratory by the dropping of rain at periodic, just the right period, to make a natural ripple tank. And here are the ripples going out, you see, and there are ripples coming back from reflection in the wall, and you can see the fan of equal time intervals like this. These are all roughly hyperbole. You can see quite a lot of detail in that picture. I put it into almost I thought you might like to see it. You sometimes see these things accidentally in nature. It's always worth keeping one's eyes open. The next slide shows how the Germans use a rather similar system. It looks different, but when you get very far away from the actual transmitting aerials, which in this case are close together, these hyperbole become straight lines. And they set up a fan of beams south of Brest, another fan of beams in northwest Spain, like this, so that they could have an imaginary grid for their aircraft and U-boats covering the Bay of Biscay. And there are many of these methods. Basically, the Decker navigator, which we were talking about the other day, employs a rather similar principle. The next slide shows the one we saw last time. In fact, our setup with 3 stations like that for setting up a double family of hyperbole, particularly for our landings on D-Day. And we might just go on to the next slide as a check. That's the point at which I want to tell you about something been happening in the last few years. The system being used developed by the Aerospace Corporation in America to make the ultimate, at least for the foreseeable future, in this class of navigation. But now one doesn't use fixed stations, one uses satellites. And although they're moving at speeds of the order of 10,000 miles an hour around the Earth, in orbits, 12-hour orbits in fact, their positions are known so precisely by measurements from the ground, and each one of them has 3 atomic clocks in it, keeping time to 1 part in 10 million. All atomic clocks, 3 atomic clocks in each satellite, and they're going to use 18 of them. They wanted 24, but they decided they can now do with 18. And you've got to have so many, and these are going around the Earth in these 12-hour orbits, that at any one point you can see 4 of them. If you've got 3 near the horizon and 1 more or less directly overhead, you've got a more or less perfect setup in 3 dimensions. And by measuring getting the signals here and measuring the Doppler effect between your observer point here and the satellites, you can get measurements both of your own velocity and your position, and the accuracy is astonishing. The design performance is that in 3 dimensions, any point on the Earth, you could establish your position to 10 meters. In fact, the trials have been coming out at much more like an average error of 4 meters in all 3 dimensions. Had the satellite positions been right, there are only a few up at the moment, and there are only 4 in view from here about between 3 and 4 o'clock in the morning. We didn't think you wanted to come back at this time to see it in any way. You wouldn't see very much other than a mysterious black box, but inside that box is all the analytical equipment for decoding the signals and producing the answer as to where you are, how fast you're moving, and in which direction. And the whole thing has to be so very precise that each satellite, as it comes past, is followed by tracking stations on the ground and say where it is. It's monitored into here, and any corrections, and you do get corrections because satellites go rather fast and rather slow depending on the gravitational pull of the Earth, which is rather different because of mountain ranges and so forth. All that data is updated into the satellite so that its signals that it comes down to you are already corrected because they've been checked every time it's gone round. And in this system, one hopes, well, it's more than hope, it's achieved. A worldwide system which, of course, would have enormous military uses, but also navigational uses too for civil applications of all kinds, and it is a very powerful one indeed. But it is a radio method, and all radio methods are somewhat vulnerable because you've got to have very sensitive receivers, and someone who wishes to can interfere to a greater or less extent by sending false signals or signals so strong that you can't hear the ones that you're looking for. And we'll take the case of radar, where the same thing applies. And here was a British radar some years ago, and you can see it's centered somewhere here. It is now so good that it picks up birds as well as aircraft. And indeed, these great rings were from birds. They were from starlings flying out shortly after dawn to their feeding grounds. No one knows why it is that the starlings are so disciplined that they fly out at more or less constant speeds, and some of them go to one part of the compass and others at others. And you can see successive waves of starlings coming out. Well, that is the picture that you would see on a radar screen. And there's one point of technique that I'd like a volunteer to come out. Well, you come, you're closest. Thanks very much. And I want you to turn the other way. And because what I'm going to do, if you were to stand over there, and in fact, you all may like to do this. All you need to do is don't cheat, just shut your eyes. And I'm going to hide this ball somewhere on the bench, you see. And now if you like to look, and I tell you it's somewhere on the bench, where would you like to look for it? Have a guess. Under here. Yeah. Well, it isn't under any there. It's in here, you see. The lesson I want you, thank you very much. The lesson I want to learn you to learn from this is something I suppose I learned almost, a proverb, that one of the best ways of hiding a pebble is to put it on the beach. And this is what we do, in fact, in radio countermeasures. We can't stop the enemy getting an echo from us if we're flying in an aircraft. But what we can do is the Americans are getting some way with that, but they're not really very far. Instead, what you do is, instead of allowing yourself to stick out like a sore thumb, you put so many other echoes onto the screen that the German controller cannot see you in time, because he's got to look at so many before he can pick out the right one. And you can do it in two ways. One, by cutting aluminium strips to a length which will resonate to the waves coming in and therefore re-radiate very effectively. And so a bundle of strips weighing perhaps half a pound would give as much of an echo as a whole Lancaster. And the other way is that was called window by us and chaff by the Americans. And here is a German radar screen with both ordinary jamming, which can be done by having transmitters in selected aircraft. And again, the Air Marshal was very much concerned with this in 100 group towards the end of the war. And here are the 100 group jammers, like that you see. They only jam along a particular bearing when the radar station is looking at them. But here are the clouds of resonators, window, dropped, and by the first bombers, and all the others can hide inside them. And the ground radar and the night fighters, to a large extent, couldn't see them. It was the radar equivalent of a smokescreen. So radio methods are vulnerable. And even though window was first used in 1943, it is still one of the most powerful of countermeasures. And the whole situation has developed so much that the American Air Force has a whole command now doing nothing but electronic warfare. And the American services, the three services between them, their budget on this electronic warfare and counter-warfare alone is now about $5,000 million a year. So you can see there could be a great premium on methods which did not depend on the use of radio in one form or another. And there is, in fact, a possibility which was first exploited by the Germans. Can we have the next slide? And before we get to that, let me just say that radar and radio methods have evolved to the stage, and here I think we've all seen these marvellous photographs. Among the most impressive, certainly the most impressive ever taken of Saturn, where the Voyager spacecraft was navigated, directed through space, clean through the rings of Saturn, and is now out beyond. But when you remember that one has to get the range of the spacecraft and of Saturn and get instructions out, and it takes 4,000 seconds for the instructions to go one way or the other. Here's a very beautiful photograph taken from an angle, of course, we could never have seen before, as the spacecraft has gone behind Saturn. The Sun is, of course, over there, Saturn and its rings. These give you, well, they're an astonishing tribute to what you can do with radio methods, providing that someone is not trying to interfere. But in the presence or possible presence of interference, and this could be natural as well as artificial from an enemy, one would like another method. But I think there is time to tell you about radar in the natural world. And so we'll spend 2 or 3 minutes on this, because it turns out that radar has been used for millions of years, not with radio waves, but with sound waves by these familiar animals, the bats. It was known for many years, of course, that they were extraordinarily good at not flying into obstacles. But thanks again to the development of ultrasonic sensors, it was possible now to listen and hear the pulses which were sent out by the bats. They're very complex pulses, and there's a lot of information. They're both pulses, and also each pulse has a succession of waves which are of increasingly long spacing, so the frequency is changing. Frequencies of the order of 100,000 cycles per second, perhaps from this case from 90,000 down to 45,000. And so they're using both the Doppler effect at least the frequency modulation effect, as well as pulse, a very sophisticated combination of both. And they can use this information in the form of the echoes coming back from obstacles, and we have some idea of the range at which they can detect. Because the bat has one characteristic which we only developed relatively lately in radar, and that was what was known as adaptive radar, that when you know there's something happening, when you first got a signal of some sort, you can pay more attention to it. And the bat pays more attention by changing the pulse repetition rate. For example, one variety of bat, it may be this one, normally pulses at 12 pulses a second. But when some information has come in through his first system that there is something ahead of him, he switches his pulse repetition rate up to about 50. So he can get more information because he's taking more observations in the same time. And by listening and hearing the switch in the pulse frequency, you know when the bat is detected. And with a 3 millimeter wire, and this is, will be about half the diameter of this, at 2 meters, you can hear that bat change to realizing there's something ahead, he's got to get more information about it. And that's for 2 meters for a 3 millimeter wire. A wire just about 0.2 millimeters diameter, the same sort of thing happens when the bat gets within 90 centimeters. And that, of course, gives him plenty of time. He's very maneuverable indeed with his wings. And, of course, he uses it not only to fly and avoid obstacles in the dark, but to catch his prey, which he scoops up like this. And what can the prey do? Well, he can do exactly what aircraft do in the presence of enemy fighters, and that is to drop down to ground level, and so that the echoes coming back are mixed up with the echoes coming from the ground. And this is why one of the reasons why one flies at low level on dangerous missions. The other thing is to do what I was talking about before, and that is to provide some jamming. And some varieties of moths which are not equipped with jammers have to evade by trying to drop out of the sky. The other variety in this class of the arctiids, they do it, they provide jamming, that when they hear the bat signals, the bat flying in and it emitting his ultrasonic pulses, there's an almost automatic, in fact probably completely automatic mechanism by which, with this organ on their thorax, they can squeeze air out quite suddenly like that and make a series of clicks. And on the next slide, you can see both a natural bat cry, an artificial one, because it's quite easy to simulate these fairly closely. And on this side, you see the bat cry, and you also get, you see, first of all, the moth echo, and you can see the clicking jammer come in as the moth has heard the cry itself, now switches on its jammer like that. And so you see this kind of countermeasure warfare has been going on in the natural world for millions of years. Well, now let us go to the prize to be had if we could only make some system which did not depend on emitting radiation. And it is possible in principle, but things that are possible in principle can be very difficult in practice. Many of you, if you've been in a tube train or anywhere where anyone's hung out an umbrella, but the strap hangers in a tube train, you can see it at once. As the train accelerates, they tend to get left behind. And as it stops, like that, as it stops, they tend to overswing. And that is because the inertia of the umbrella, if it's hanging up, or the strap hanger, it tends to get the mass center left behind like that until there's no more acceleration. It then should go along like this, but of course in the vibration of the train it doesn't usually stay as steady as that. And as the train slows up, the inertia causes it to overshoot. And so from the angle of trail or overshoot, you can get a rough measure of the acceleration and deceleration. And you can get the same thing, and this is in a more convenient form, many ways, if you've got a mass and a spring, and you start to pull it like that. While it's accelerating, the spring is stretched. And as it decelerates again, you'll see the spring is now stretched, it catches up, and as I cause it to decelerate, or the system to decelerate, the spring compresses, and you see in principle from the extension of the spring, or you can measure its acceleration, the compression of the spring, its deceleration. And this very crude idea gives one a method of measuring acceleration depending on the inertia that mass has. Well, it's a very far cry indeed from that crude idea to a feasible method of measuring position. But you see, how many of you have done any calculus? Right. Well, you know that if you integrate acceleration, you can get velocity. And if you do a double integration, if you integrate all the history of accelerations, you'll get your velocity at any one time. And if you do a double integration, integrate up all the velocities, you will get the total displacement. And provided that you have done everything correctly from the point of origin, you will be able to tell how far you are by this double integration, having the right constants, how far you are from your point of origin. And if you have three of these things at right angles, in principle, you can do it in all three dimensions. You can use this, or if you're content with radar, if you risk radar, you can use the Doppler effect to give the same, because that gives you velocity directly. But the most interesting devices are those using inertia. And there are many ways in which it was done. The first one, I think, was in the next slide. It was employed in the German V2 rocket, where they did use Doppler on radio to get velocity in some of the rockets, but in many of them they had integrating accelerometers, as these devices are called, to give them both velocity and, I think, displacement. Anyway, that was the start of the technique. As with so many things that have happened since, the effort the Germans put into the V2 militarily was silly, but technologically marvelous. And one of the results, of course, has been all the space developments ever since. And the idea of integrating accelerometers caught on. And in this country, we have at least two companies who make these devices astonishingly well. And one of them is Ferranti. And if this, I'm afraid, will look terribly dull, because it just looks, it literally is, you see, a black box. And without, I hope, insulting Ferranti, not a particularly elegant black box, but that is largely because it has done so much work. If I were to tell you inside there are some of the most precise gyroscopes in the world, which stabilize a platform in 3 dimensions, and then on that platform are 3 accelerometers, working really in this way for the X, Y, and Z directions, and can do it so well that a very similar aircraft to that goes into our Harrier and Tornado aircraft. And that equipment itself surveyed for the government all the A roads in Scotland in 3 months, much the best way when you're going uphill and down dale, and very difficult to triangulate. This equipment went around made a new map of all the main roads of Scotland inside 3 months. It's been down here. It did the motorways, the trunkways, all the A roads, all the B roads in Kent in 3 months. It's been in a miniature submarine under the North Sea, tracing pipelines accurately, and also now a similar version, or rather similar version, can go down the boreholes in the drills in the North Sea to tell exactly where the drill has been going. All we can show here, and remembering this, if you've thrown an aeroplane all over the sky, as the Harrier does, and I saw them operating some years ago in Belize, and the pilots were tremendously enthusiastic because they could do the most tense and strenuous maneuvers, throwing the aeroplane all over the sky, and at the end of it, the gyroscopes had still coped, and there was the navigator telling them precisely where they were over long areas of jungle where otherwise they would have had the greatest difficulty in knowing, and doing it to such an accuracy that when employed, for example, on a civil aircraft going across the Atlantic, its drift would be no more than about 5 miles out. The error you would get from estimating your position only 5 miles out after crossing the Atlantic. And you see no radio aids, no need to look at the stars, anything else. It is a most impressive development. And all we can show you here, remembering that this same thing will cope with hundreds of miles an hour, is a small movement across the lecture room where I should hope the scale is reading roughly, is it, Stuart, in centimetres now? And if you could move it across for us. Mr. Wilson has come down from Ferranti to demonstrate it for us. And now if the camera can get a good view, can it, of the... This is the presentation which a Harrier pilot would have. I think that's right to say, fair to say. And it would, it would not only tell him where he has moved, but will also tell him when a target is put in, where the coordinates of a target, where he ought to go, with all the computing facilities which are available. And we're running all right, Al? Yes. There you can see the last figure there is its centimetres. And so what it is doing is really measuring position by integrating up to, as in this case, the nearest centimetre. And its performance can be expressed in rather another way, which is interesting, that because it has a gravity factor in it, you can regard it as establishing the movement by the fact that at this end of the bench, the vertical down to the centre of the Earth will be there, and because the Earth is somewhat curved, and it will automatically find the level, it will tell the amount of angle you've got to move from the one part of the Earth to the other, and even such a small angle as between the ends of this bench, you'll see it will detect quite easily. That is how sensitive it is to the changes in the local level. And so I hope that came up all right on the screen, did it? Well, thank you very much. And yes, I again mustn't waste too much time, but may I say, one of the fascinating things about all these studies is that time after time, when one finds that one has solved a problem, either for military or civil purposes, you look into the natural world and you find that other animals in nature have solved the same problem. No animal that I know of has actually made an integrating accelerometer, but some have got gyroscopes. And if you catch, you know, how many of you know the daddy long legs or crane fly? Right. Well, if you look at the daddy long legs, and do so next time you get a chance, you'll find that they have got only one pair of wings. Many insects have got two pairs of wings. They're called diptera or diptera, meaning two-winged. And what has happened to their other two wings? The answer is that they're no longer wings. They're like two little drumsticks sticking out from the thorax, which you can see. And for a long time, it was a mystery. It was known that if you removed them, the insect couldn't fly. But they are, in fact, a very interesting form of gyroscope, depending on the fact that if you have a rod like that and you want to turn it, it's very easy. If you have it like that, and you've got to do a good deal more effort to turn it. And so if you've got something oscillating backwards and forwards like that, which they have in sympathy with the wings, it is more easy to turn while it's in this part of the arc than when it's in that part of the arc. This gives rise to forces at the bottom here, which are sensed by nerves. And it is, in fact, a design from which a new type of tuning fork was developed, called the tuning fork gyroscope, because a tuning fork does exactly the same sort of thing, which turned out to have a very good performance. It didn't quite make it, because in the meantime, ordinary gyroscopes become so good because of their bearings, but there was actually a human development inspired by the recognition that the daddy longlegs stabilized itself in flight by means of these tuning fork gyroscopes. Well, that's a very quick aside, because what I want to talk about for the last few minutes of this lecture is another development which I myself have certainly been, as it were, either involved in or watching for the last, 39 years now. And, no, I beg your pardon, 49 years. Oh dear, we are old, aren't we? Anyway, I started research in infrared in 1932, and I got involved in trying to detect aircraft before World War II by the heat radiation which they emitted. And one of the targets, or one of the objectives that some of us would like to have done, was to, instead of simply measuring on a meter the amount of extra radiation coming out of a hot target, would be to display it on a picture. And the first people to succeed in that were the Germans. Again, a military development, and they were wondering whether they could make a system to fly over a country and detect towns by the heat which they emitted. And this is how far the Germans got. By having a detector of heat radiation, which would warm up very slightly whenever heat fell on it, and making a scan of a cathode, or it wasn't a cathode ray tube, it was a photographic plate, in sympathy with the heat signals coming. You see, they built up very laboriously, but very good for the time it was done, 1943 or 1944. And here you see, here's one of the research people, open neck shirt, shirt sleeves rolled up, because his shirt is cooler and is radiating less than his forearms or his face and his open V-neck. It's a bit tight on his shoulders, as you can see, because it's stretched in contact there, a bit warmer. And that was the stage reached by the Germans at the end of World War II. Well, since World War II, largely because of the military value once again, there was been very intense developments in our own country, in America, and certainly in Russia. And the state of the art now, I think, is best exemplified by what is undoubtedly the best, as we say, thermal image detector or picture maker in the world, which is made by the firm of Barr and Stroud. And we'll just look at two of the most dramatic pictures, one of which is of a jumbo jet at night, taken by what light was available at the airport. The next slide shows a picture taken from exactly the same position, but taken by this camera, which is recording not the light, but the heat being radiated by the different things that it can see. And you can see that the aircraft itself is slightly warm with respect to the background. At least most of it is. Its tailplane here isn't, you see, but there you can see. And you can see the detail. You can see which airline it belongs to. And these improvements, which have taken place in the last 2 or 3 years, really have changed the situation out of recognition. And we can now actually, with this camera, which is here, have a look and see what it can see. And if someone will come and operate the camera, its visual presentation is here, but it's entirely compatible with the BBC television, and the signals can be fed straight in, and so we'll be able to see them on the monitor. And now you see we've got no light pretty well in the lecture room, and there you are, all radiating. Your faces, well, would you like to hold your hands up? And you see at once, there are your hands showing up, or wave them about. Even separate fingers are being seen, you see, like that. And so you can see, for example, if you're guarding a site where you might have intruders, this will give you a very good picture in complete darkness, purely by the heat radiation coming off the, even just one's face, like that. There are various things it may do. If I can find, oh, here's a sponge. I'll go out in front for the moment, and one can, you see, because water evaporating loses its fastest molecules, like that, a wet surface is always slightly cooler than the surface, than the body of the thing and the things around it. And there you can see immediately that the sponge is really quite cold, because you see my hand is quite warm, but this is blacker than anything else it can see, just because of the slight lowering in surface temperature because of the cooling produced by evaporation. So there is that. I wonder what happens if we put this in front of it. Yes, this is beautiful. You see now, we see the Royal Institution as black on white, you see? Now, much of that difference is not due to the fact that those letters are at a different temperature. It may be partly that. But one of the effects, which is very clear here, is that the black is showing up there. Whereas if we have the visual picture, and I think we now have the lights up, you see it in fact is light on dark. And the reason is that, and it's a very, you probably learned this rule, but who know the rules that good absorbers make good radiators? Well, you see, here is the case in point. The black is a good absorber. The metal is a good reflector, bad radiator, and the thermal picture, you see, shows it quite correctly the other way round, because the black is radiating more effectively than the white. Well, this has been a peculiarly Scottish occasion. We've had Messrs. Ferranti from Edinburgh, Messrs. Barnes-Stroud, that was Stephen Wilson from Ferranti, and Mr. Lorimer and Mr. Sutherland from Barnes-Stroud, and indeed Glasgow, Edinburgh, my own laboratory, and my colleague Mr. Barber, who made all those beautiful instruments you saw in some of the earlier lectures, and so forth. And this is the season of Hogmanay. Now, you know what Scotsmen think of Hogmanay. It's a time to be with their families and their friends, and nevertheless, they have sacrificed that to be with us tonight. And so I'd like the applause this time, not to be for me, but for these colleagues from my own university, from the two firms, Ferranti, Edinburgh, and from Barnes-Stroud in Glasgow. And I'd like to say thank them very much, and a Happy New Year to them all.